Okay. Here's a question. Do you recognize what these things are?
Few bugs.
You know, in the back, you're a little far away. Anyone have any idea what these are? Anyone ever heard of a game called Risk?
Oh, yeah.
This is the new version. The old version was made out of wood, but you know, wood used to be cheap. Now plastic is cheap. My dad bought a car in 1964, and the dashboard had wood on it. See that anymore. Get rid of it. Unless you like drive a, I don't know, maybe a Rolls Royce or something. Wood was cheap, but plastic isn't. But okay, so there are two of them. Does anyone know? Okay, from Risk, what are these things in Risk? Anybody know what these are in Risk, the game? Nobody? You guys don't play Risk, I guess. Fun. It takes hours and hours, and then it's all over in like 2 minutes. It's a board game, and it's kind of abstract war. Vincent, is he Vincent here? No. Okay, wait. Trying this. Kayla. So it's a board game, and they're like countries, and you put armies. These are armies. This is one army. Well, it's actually just a piece of plastic, but you know, that's how games work. And most of the game, you play with these. And then towards the end, things heat up. So this is, anyone know how many armies? It's called a Death Star. Because when you start using these, it's getting close to the end. This is 10 armies. Yeah. So since none of you know what this is, my prop is totally falling flat, right? You got 1 and then 10. So we don't do that exactly with numbers, do we? We have like there's 8, right? And this isn't really 2, right? It's 2 Death Stars, right? It's 20, right? And then 6, that's 6. It's not 6, it's 600. It's very convenient. And when we do arithmetic, we take advantage of this place location thing, right? It's one of the reasons we need a 0, right? If I had like 605, I can't write that this way, right? I need a 0 in there. So, does anyone here, I can't imagine, but I have to ask, does anyone here not know long division? embarrassed. Now, maybe everyone knows long division. Maybe some people are not so good at it. Maybe, I don't know. I mean, I know they've de-emphasized it in the last 40 years since I took it. 50 years. But let's just go through a problem for a second, because I want to make sure we're all on the same page here. So I say, well, 4 goes into 6. So it goes in one time. And I know everybody knows this. Okay? You multiply, and then you subtract. Well, you could bring it all down, but usually you just bring down the second next number. And then we repeat, right? 4 goes into 22. Well, that's going to go in 5 times. And then we do this one more time. And we get 7. And since we have 0 here, we have no remainder. Right? If we had a remainder, we might write that as remainder 0. Or we might write it as 0 over 4. Right? So that's the way we do long division. But we're using this placeholder thing here. I wonder if it would be really different if we were a little more explicit. Like, let me rewrite this. It's 6, 2, 8, and 2. That's really 20. So I'm just going to put a little t here for 10. Maybe I'll put a 1 next to it, 110. And then next to the 6, we have 2 10s. And then next to the 8, I have no 10s. Okay. So now I can do my long division, right? And 4 goes into 6, 4, not 4, 1. 1 t squared, and now I have 4 t squared. 2 t squared, bring down my 2t. And same thing, right? This is just going to put a plus in there for the moment. Plus 5, so that's, well, this is 5t, right? And this is a t, so it's 20t squared, or it's not 20t squared, is it? No, this is t0, okay. This is really complicated and awkward, right? I mean, I can't even do it quite right here. We know where we're going, right? So we don't really want to do that, do we? That would be a pain in the neck. But the subject for today is dividing polynomials. And when we divide polynomials, we have something like this going on here, no? So I wanted to divide, say, 6x squared. That's a lot like t squared, doesn't it? Minus 26x plus 12. We want to divide that by x minus 4. I don't know why I'm trying to pull the blank here. Hold on. Paul. Paul usually sits there. I have no idea. Are you here, Stefan? Okay. Did you do something with your hair? That's what you do. Okay. So we have a technique for doing this, but like what I was trying to show you before, it's kind of it's a little awkward. Again, we would try 6x squared. Many of you have trouble with minus signs. Now, if you feel okay about what you're doing, fine. But if you have trouble with minus signs, instead of writing minus 26x, I'm going to recommend you do the following: plus minus 26x. This is just to avoid simple, careless errors. It's just a discipline that may help. Plus 12. And now I'm going to divide this by x minus 4. Or again, for those of you who may have a little trouble with minuses, you could say plus minus 4. And, you know, we look and say, well, how many times does x go into 6x squared? And the value we're looking for here is 6x. So now we go through this process we're used to. 6x times x is 6x squared, just like we wanted. 6x times minus 4 is minus 24x. Now I'm not like confused about what's plus and minus. These are minuses, right? Minus 26 minus a minus 24. Right? Minus a minus 24. So that's plus 24. So minus 2x. When I do this, I feel like I must be making simple errors because I'm trying to talk and chew gum at the same time. But anyway, okay, let's try minus plus minus 2 now here. So minus 2x minus minus, so plus 8, subtract 4. And now I have a remainder 4, or 4 over x minus 4. Okay. That's doing polynomial division the long way, long division. I'll call it the old-fashioned way. That's the way I learned it. I kind of like it, even though it's a little complicated and awkward, but it gets the job done. We're going to look at an alternative in a little bit, but it has an advantage over the alternative, which is the alternative. This is long division. The advantage is over synthetic division. As far as I know, with synthetic division, it's only good if you have something like this: x minus 4, or x plus c, or x minus c. If you have something of a higher degree, I don't think synthetic division works. I've never seen how it can work. My notes have a different answer here. Oh, darn. Yeah, this should be plus. That one's really, yeah, this should, oh, I guess my notes are wrong. All right, that's fine. I did it right on the board. Okay, don't look at my notes. All right. So, for example, let's say I have something like this. 8x to the fourth plus 6x squared minus 3x plus 1. And I want to divide it by 2x squared minus x plus 2. Now you'll notice I left room here because unlike with regular division where we have a 0 in there automatically, with polynomials we might not, but we don't want to miss out on that. We want to be orderly. All right, let's see if I can do this one right. This will be 4x squared, 8x to the fourth, minus x cubed plus 2x squared. So 0, 0 minus a minus is x cubed, 6 minus 2 is 4x squared, minus 3x. This will be, how's that going to work? How am I going to do that? Well, I guess I have to put a half, right? X cubed minus a half x squared. This is kind of awkward. Plus x. So 4 minus a minus is 9 halves x squared minus 3 minus x minus 4x plus 1. So now what do I need here? I need 9/4. Minus 9/4 x. That's 9/2. Okay. Oh, fractions. Minus 16/4 minus 9/4 is going to be minus 7/4 x plus 1 minus, or 2 halves minus 9 halves is going to be minus 7 halves. So that's my remainder, minus 7/4. This should have come out better, shouldn't it? Over 2x squared minus x plus 2. So again, it can be a little awkward, but it kind of gets you through the ugly stuff. All right, any questions about, long polynomial division? You might think to yourself, well, how do I check this? Well, you might check it the same way you would check regular division. You can multiply this by this, and add the remainder and see if you get what you started with. That's always a good idea. All right, that's long division. But time moves on and something maybe better came along called synthetic division. Now, let me just say something. You do have to know long polynomial division because, as I said, synthetic doesn't always work. You don't have to know synthetic division because you can just do it the other way. There's no point in me saying you have to know how to do something 2 ways if there's no point. However, some think it's much easier or less likely to have errors. So let's look at a problem, how we would do it using synthetic division. So the way we set this up is you write down the coefficients of polynomial 2 minus 7. Oh, there's an x missing, so we have to put a 0 and a 5. By the way, I'm willing to bet at least somebody in this class knows how to do this better than me. He said, when I grew up in the dark ages, we didn't have this. Now here, instead of x minus 3, we're going to put 3. One way to think about this is x minus 3 goes into this, then 3 is a root of this, right? Okay, so how do we do this? So we take 3 and we multiply it by 2 and we write it over here. And then we add. That was really simple. Take 3, multiply it by minus 1, minus 3, we add. Take 3, multiply it by minus 3, that's minus 9, we add. Now we're done, but now we have to know how to interpret this. Well, oh, I forgot to bring the 2 down. So what this tells us, these are the coefficients. 2x squared minus x minus 3, and then this is our remainder. So minus 4 over 2x cubed minus 7x squared plus 5. Did I get that right? Well, somebody knows this better than me. The other way you might want to think about it is 2x cubed minus 7x squared plus 5. What we started with is x minus 3 times 2x squared minus x minus 3 minus 4. Okay, right? This is equal to this. I multiply through by x minus 3, and oh, I'm sorry. I didn't get it right. Nobody caught me. This is the remainder. Now I have a problem with synthetic division. I don't know what I'm doing. Anybody know what I'm doing when I do synthetic division? I mean, it comes out right. I really want to know what I'm doing. Well, I do, because I figured it out. And I want to show it to you, but first we have to do a little work. So, what we're going to look at, I think I'm going to leave this here. This is going to come in handy in a little bit. But what we're going to look at is what's called the remainder theorem. Has anyone heard of the remainder theorem before? I mean, you kind of use the remainder theorem in a simple form. Let's take something like, we'll just take 7 divided by 3. So 7 divided by 3, 2, 6, remainder 1. So what do we mean by this? What we mean is 7 divided by 3 is 2, plus the remainder divided by 3. Which we also could write as 7 equals 3 times 2 plus 1. Everybody see how that is? In other words, this is kind of a statement of what dividing 7 by 3 is, right? We're going to divide 7 by 3, we're going to divide 2 times, and we're going to get a remainder. Well, it turns out the same thing is true for polynomials. If I take a polynomial, px, and I'm going to divide it by a first-degree polynomial. That's how synthetic division works. It only works for the first-degree polynomial. I'm going to get another polynomial. Now, if this polynomial is of degree n, let's put a little n here, then this can be no more than n minus 1. By dividing it, I'm reducing its degree. And then I might get a remainder, which can divide by x minus c. And similarly to when I'm using numbers, I could rewrite this as e to the x equals x minus c q of x plus r. Where again, we know that q has a lower degree than p. Well, it really has to, right? Because we're multiplying it by an x. It's going to raise its degree. So for these to be equal. R is just a constant. There's no polynomial there at all, just a number. Could be 0. All right, well, that's just a fact. That's not the remainder theorem. Let's take a look at the remainder theorem. The remainder theorem says if we divide a polynomial p of x by x minus c, then the remainder just thought of a great invention for teachers. I'm going to have a glove. It's going to have an eraser on the back of it like this. Where I need to. The remainder is C. No, it's not C. It's P of C. Well, what do I mean by that? Let's take a really simple example. If I divide x squared plus 1 by x, right? That's, say my function, my p, the p is, p of x is x squared, right? And I'm going to divide that by x minus 0, right? Well, the remainder theorem says that the remainder I get, which is obviously 1, is the same as if I plug in 0 here, I get 1. Now that example was so simple, it might even disguise what's happening. instead I had, say, x to the 5th minus 3x squared plus 2, and I want to divide that by, say, x minus 5, and I want to know what the remainder is. The remainder theorem says all I have to do is plug 5 in here, and I'll get that remainder. Let's see, 5 to the 5th. 5 to the 5th is, it's a big number. We're not going to do that problem. But it'd be nice to know that this is true in general. So we're going to prove that right now. So going back to the fact that if you divide p of x by x minus c, you get some polynomial plus remainder divided by that x minus c. I can rewrite this way. Right? This is true of any polynomial. Right? If I divide it by some x minus c, I'm going to get a smaller polynomial, a lower degree polynomial plus remainder. So let's see what happens when I plug in c here. I get p of c equals c minus c times q of c plus r. This is a really simple proof. What's c minus c? That's 0. 0 times anything is 0. So I have immediately that p of c equals r. That's my remainder theorem. Right? Again, it tells me I want to divide a polynomial by x minus some number, and I want to know what the remainder is. I just can plug c into the polynomial and I can find out what it is. All right, there's a corollary to the remainder theorem. Does anyone know what a corollary is? Remember? Aaron, do you remember what a corollary is? Sophie? Alexis, do you remember what a corollary is?
I've never heard of it in my life.
Have you taken geometry?
Yes.
Ah, you know what a theorem is, right?
Yes.
Corollary is a type of theorem. It's actually just a plain old theorem, except it's got something special about it.
It says on the lesson plan. On the lesson plan it says it's the remainder theorem.
Well, I'm saying we're going to have a theorem. It's called the factor theorem. And I'm calling it a corollary instead of a theorem, because it is a theorem. All right, a new vocabulary word. A corollary is a theorem. It's just a simple consequence of another theorem. And the factor theorem is a simple consequence of the remainder theorem. You know, the remainder theorem, the factor theorem is less complicated and it kind of follows from it. Let's erase here so you can see the factor theorem in all its glory. Factor theorem says C is a zero of P, meaning, P of X, if and only if, now I have to ask a question again, is Everyone seen this abbreviation? IFF? If and only if x minus c is a factor of p of x. Does anyone know what I mean when I say if and only if? Like in terms of theorems and proofs? Kayla, do you know what if and only if means? Be brave. Can't, you can only get it wrong. That's the worst that could happen.
But it's like the only.
Okay, that's fine. Nobody else is answering. Who here didn't take geometry? Yeah, everybody took geometry. Oh, I'm going to do a little research. Who here took geometry and never did a proof in geometry? Okay, so everybody did a proof, right? Maybe. Why? If and only if is so long ago.
They like specific to one condition.
Oh, it wasn't that long ago. Like I took geometry and that was a long time ago.
So if and only is specific to one condition, it's not going to execute it.
Okay, let me tell you what if and only is. It means really there are two theorems here. It says C is a zero of P if x minus C is a factor of P of x. And the opposite, if x minus C is a factor of P of x, then C is a zero of P. Not all theorems go that way, right? I mean, sometimes you can say if A is true, then B is true, but B could be true and A could be false. I don't have it one top of my head, but maybe I'll think of one before classes. Okay, so we really need to show two things to show this is the case. So let's go back. Let's look at this again. We have P of x, and we know that it's going to be some Q of x of lower degree times x minus c plus some remainder. So if C is a zero of P, C is a zero of P, what is that? That means P of x equals P of C equals 0, right? So C is a 0 of P. It's equal to Q of C times C minus C plus what? What's the remainder have to be? This is 0. 0 plus the remainder is 0. So what's the remainder have to be? Now I know you've all taken basic arithmetic here. Let me rewrite this. 0 plus r equals 0. So what does r equal?
0.
0. Okay, good. That's scared there. So that means that P of x equals Q of x times x minus c, because r is 0. But that means x minus c is a factor of P of x. Right? That's the first part of this theorem. That comes from the remainder theorem. All right? This is the factor theorem. Okay, we're halfway there. What if x minus c is a factor of P of x? Well, that means P of x is x minus c times some other polynomial. Right? But if that's the case, what's p of c? C minus c times q of c. That has to be 0. So if this is true, then c is a 0 of p. I'm stepping over some bounds here. I know students like, some students in math, they just want to know how to do it. Don't really want to know how it's done. But and that's fine. But to really appreciate math, you kind of have to see it. It's not just a bunch of rules that we give you to learn, like in French. You know, like when to use the plus positive, or I have all those tenses, right? I never could figure out when to use them. Well, the past is the past, and the future, but what's perfect about it? Okay. All right, so remember I left this up on the board here. I want to digress a little here for a second. How many, I know there's a bunch, how many computer science people are in? 1, 2, 3, okay, at least a third, yeah. Computer science people, pay attention. This is almost like a computer science class coming up here. When you see some expression like this, let's say 3 plus 5 times 7 minus, let's say 6 times 2 plus 3 times 4 minus, okay. Now, those are times, not x, not variables. You could do that, right? Everybody here could do that, no problem. There's not even ambiguity involved, right? Like if you see this, times 7, then you have to go, wait, what do I do first? Add first. Which convention am I using? I'm using left to right, or am I using, you know, my Aunt Sally, whatever? But if you feed this to a computer, the computer has a problem. It knows how to add, knows how to multiply. It doesn't know how to parentheses. I mean, check your manual on machine code. There's no parenthesis instruction. So what's a computer to do? Well, we actually can give this statement to a computer, but what happens? We need to write it in some, not the machine language, some other language. What's another language we might write a computer program in? JavaScript, good example. Yeah. And somehow JavaScript turns this into something the computer can figure out. Does anyone know the name of the thing we use to turn it into something the computer can understand? That's what we turn it into. Who turns it into pseudocode? Yes, an interpreter. Or a compiler could. Inside the interpreter and the compiler, there's this guy called a parser. Heard of a parser? Okay, so what does the parser do? He's got to turn this into something the computer can do. And there's a name for a certain kind of parser I'm thinking of. A certain kind of parser will do the following. It'll say push 3, push 5, add. So it'll like push 2 numbers into what we call a stack, and then when you say add, it adds those numbers. Okay, and then we might say push 6 and push 2, we might say multiply. Right, that'll get us this. But now we've got what? We've got 8 on the stack, and we've got 12. We could say subtract. Then we'll subtract. Oh, I forgot to multiply by 7. No, bad parser. Push 7, multiply. And then I'll push my 6 into. So the computer, you know, we have a program called a parser that changes this so that it's something the computer can do. This particular form of parsing, we parse it into something called RPN. You know what that stands for? Reverse. This is going to have something to do with all you non-computer people. I know I'm putting you to sleep, but this will fit in just a minute. Reverse, reverse, Polish notation. Well, something's reversed about it. We don't say 3 plus 5. We say 3, 5 plus 7 multiply. Do it kind of backwards. Okay. There's a neat language that you won't run into called forth. F-O-R-T-H. Computer people might want to look at that. That's all you do in forth is you do RPN. All right. So let's get back to this this problem here. 2x cubed minus 7x squared plus 0x plus 5, and I'm going to divide that by x minus 3. But first I want to change the polynomial here a little bit. I want to rewrite it. First thing I want to do is take an x out. I can't take it out of all 4 things, but I can take it out of 3. So I get 2x squared minus 7x plus 0, and then plus 5 over here. And then I want to do that again. I'm going to take an x out, 2x minus 7 plus 0 plus 5. Okay. I want everyone to look at this and convince yourself that this is the same as this, isn't it? Right? They just manipulated a little, but it's the same. So now what I want to do, I'm going to plug 3. I'm going to plug 3 into this. I'm going to do it very carefully, step by step. I'm going to start in the center. So I'm going to say x, x. Eventually I'll plug it in everywhere, but I just want you to see what I'm doing. 2 times 3 minus 7 plus 0 plus 5. Which, I mean, it's pretty easy. It's 2, 3, multiply, 7, subtract. Two times 3 multiply, that's 6, right? And then I'm going to add it to -7, right? Okay, you rewrite that. X minus 1 plus 0 plus 1. Oh. Note that when we divide x minus 3 into this, the first coefficient is 2. You got that here. And then the result, then the next coefficient is -1.
Yeah, I
You
know.
got that here. So we got here and here.
Okay.
Okay, let's plug in 3 again. Right? X times 3 times -1 plus 0 plus 5. Okay. 3 times -1 plus -3. Then I'm going to add 0. That's what I'm doing here. Right, so that's minus x times -3 plus 5. All right, the last thing I'm going to do is I'm going to plug 3 in again. 3 times -3 plus 5. So over here, 3 times -3, well, that's -9. Plus 5 is -4. So finally we get -4. If you weren't paying close attention, you might have missed what happened. So I'm going to tell you what happened. I took my polynomial and I kind of rearranged it into a form that a computer would like. So I can do my arithmetic in an RPN fashion. I can just take 2 numbers and do something with them, and then take 2 numbers and do something, and so forth. But that's not the real trick here. The real trick is to realize that when I started processing this 3 here, right, over here, all I'm really doing with synthetic division is I'm plugging the number into the polynomial. Right? Where is it? The remainder theorem says if you want to know what the remainder is, just plug in the number. That's almost all I'm doing here. I'm plugging in 3 to my polynomial. That's what this calculation is, and out pops the remainder. Now, along the way, I happen to grab these coefficients, end up part of the quotient. So this isn't just something that just magically works. It's using the remainder theorem, right? We're kind of watching the process as we go along, right? But that's how synthetic division works. That was really complicated what I just said. Does anybody have any questions? It won't be on the exam before you ask. All right. Let's try and simplify things. What do you need to know about today? What do you need to know? Well, you need to know how to do long division because, as I pointed out, this isn't just a first degree. It's not going to work with synthetic division. You don't have to know, if you know how to do long division real well, you don't have to know synthetic division because you can always do long division. But maybe synthetic division is a little easier. You want to know the remainder theorem. Remainder theorem says I have a polynomial. I feel the pull. Now we got lots of time. Pull of the clock. You need to know that if you want to know the remainder when you divide one polynomial by x minus c. You just plug in c and into the polynomial. That gives you the remainder. And you should know the factor theorem, which says if p of c is 0, then x minus c is a factor, and vice versa. If x minus c is a factor, then p of c is 0. That second part is kind of obvious. If you multiply something by x minus c, you plug in c, you're going to get 0. All right, let's do something practical here. Let's just do one problem where we want to factor a polynomial. This is my polynomial. So this is a kind of a pay your money, takes your chances kind of thing. But if we can guess a 0 of this, it's going to help us. So just off the bat, well, I can try 0, plug in 0, remainder 6. That's not what I'm looking for. I'm looking for a remainder 0. But if I plug in 1, well, 1 minus 7 plus 6, that's 0. So I know that x minus 1 is a factor. This factor theorem tells me that. I'm going to say that again slowly, because this is the real pearl of wisdom for today. If I can figure out a number to plug in here that makes it 0, then I know x minus that number is a factor. And that can help me factor in this polynomial, which might not be a quadratic, right? It might be to the 4th or to the 5th. All right, let's go ahead. I'm going to do long division here. I have just enough time. 7x plus 6. X minus 1, x cubed, minus x squared, minus a minus is positive x squared, minus x plus x, x squared minus x, minus 7, minus a minus x is minus 6x, plus 6. I know that this is going to work out with no remainder, because I got a 0 here, right? So minus 6x plus 6, 0, remainder 0. So now I know my polynomial is x minus 1, x squared plus x minus 6. As soon as I get this down to a quadratic, I'm home free. I'll either be able to factor it using reverse FOIL, or worst case, quadratic formula. We'll find the zeros, which tells me what the factors are. So let's try that. Minus 1 plus or minus the square root of 1 minus a minus, so plus 24 over 2 minus 1 plus or minus square root of 25 is 5 over 2. So minus 1 minus 5 minus 6 over 2 minus 3 and minus 1 plus 5 is 2. So that tells me my factors. X plus 3, x minus 2. Okay. That's it. Thank you. Anybody I didn't catch coming in? I got you. Paul, Jada, Jackie, Leon, Powell, Yang, Sita, Bianca, Anne, Dr. Beckman, and people not here. Okay.